Crude oil is one of the world's most important natural resources. It provides the raw materials used to make fuels, plastics, lubricants, and countless other products. But despite its importance, crude oil in its natural form isn't very useful at all. So in this video, we're going to explore what fractional distillation is and how it separates crude oil into useful fractions. But before that, we first need to understand what crude oil actually is. Crude oil is a naturally occurring complex mixture of hydrocarbons found deep beneath the Earth's surface. It formed millions of years ago from the remains of tiny marine organisms that were buried under layers of sediment and subjected to high temperatures and pressures over an incredibly long period of time. Now, for A-level chemistry, you don't need to know the details of how crude oil is formed. What's much more important is understanding that crude oil is a complex mixture. It's a mixture containing hundreds, if not thousands, of different hydrocarbon molecules, all with different chain lengths and therefore different physical properties. Some of these hydrocarbon molecules are very small and contain just a few carbon atoms, whilst others are much larger molecules containing dozens of carbon atoms joined together in long chains. But the problem is that all of these hydrocarbons are mixed together. This makes crude oil not particularly useful in its raw form despite its hefty price tag. If we wanted to use crude oil to fuel a car, heat a home, or manufacture plastics, we first need a way of separating these different hydrocarbons into more useful groups. And that's exactly what fractional distillation allows us to do. Fractional distillation is the industrial process used to separate crude oil into fractions based upon their boiling points. But that immediately raises another question. What exactly is a fraction? Well, a fraction is a mixture of hydrocarbons with similar boiling points, and this is one of those really important definitions that you need to learn word for word as it commonly comes up in exam questions. Now, there's a really important piece of information in that definition that many students get caught out on, and that is that a fraction is still a mixture. Fractions aren't made up of just one hydrocarbon. They're a mixture of several different hydrocarbon molecules that have similar carbon chain lengths and therefore similar boiling points. And this means that each fraction has slightly different physical properties, and therefore each fraction has its own particular use based upon those properties. For example, one fraction might be suitable for use as petrol in car engines, whilst another is more useful as aviation fuel or diesel. So fractional distillation is the process of separating the complex mixture of hydrocarbon molecules within crude oil into groups, or fractions, based upon their boiling points. But how does the process of fractional distillation actually work? Well, the first thing that happens is that the crude oil is heated in a furnace to a very high temperature so that it vaporizes, which is just a fancy way of saying it turns it into a gas. These vapors are then fed into the bottom of a fractionating column. Unlike a simple laboratory distillation, this is a continuous industrial process, with crude oil continuously entering the column and the different fractions continuously being removed. Fractionating columns are tall metal towers containing trays or plates that allow rising vapors to pass through while collecting condensed liquids. These towers have been carefully designed to separate and collect different fractions at different levels depending upon their boiling points. Inside the column, the temperature isn't the same throughout. It's hottest at the bottom where the vapors enter the column, and it becomes gradually cooler towards the top. This gradual decrease in temperature is known as a temperature gradient, and it's one of the essential features of fractional distillation that allows the separation of the hydrocarbon molecules. As the hot hydrocarbon vapors rise through the column, they begin to cool. Eventually, each hydrocarbon reaches a point where the temperature of the column falls below that of its boiling point. When that happens, the hydrocarbon condenses back into a liquid. Once condensed, it can no longer continue rising as a vapor, so it collects at that level of the column and is drawn off as a fraction. Hydrocarbons with relatively high boiling points condense quite quickly, because the temperature lower down in the column is closer to their boiling point. As a result, they are collected lower down in the column. In contrast, hydrocarbons with lower boiling points need to cool much more before they condense. They therefore travel much further up the column before condensing and are collected much higher up. So by the time the vapours have travelled through the fractionating column, the original mixture of hydrocarbons has been separated into a series of different fractions, each containing a mixture of hydrocarbons with similar boiling points. Now that we have an understanding of exactly what happens during fractional distillation, we now need to look at the key principles that explain why this process works. Everything we've just described relies on two key ideas. The first is that the hydrocarbons within crude oil have different boiling points. If every hydrocarbon boiled and condensed at exactly the same temperature, there'd be no separation at all. But where do these different boiling points come from? Like with many organic substances, as the carbon chain length increases, so does the boiling point. The larger the molecule, the more van der Waals forces of attraction there will be acting between the molecules. This means that more energy is needed to overcome the forces of attraction, and so they have higher boiling points. That means crude oil naturally contains hydrocarbons with a wide range of different boiling points, making separation possible. But having different boiling points on its own still isn't enough. The second key idea is the temperature gradient inside the fractionating column. Remember, the column is hottest at the bottom and coolest at the top. As hydrocarbon vapours rise through the column, they experience progressively lower temperatures. This means that different hydrocarbons reach temperatures below their boiling point at different heights or levels within the column. Larger hydrocarbon molecules with their higher boiling points condense lower down, while smaller hydrocarbon molecules with their lower boiling points continue travelling further up the column before eventually condensing. And it's the combination of these two ideas that makes fractional distillation possible. Different boiling points determine when each hydrocarbon condenses, while the temperature gradient determines where in the column that happens. Without different boiling points, every hydrocarbon would condense together, and without the temperature gradient, they'd all condense in the same place. It takes both of these key ideas working together to separate crude oil into useful fractions. Now that we understand how fractional distillation works, let's have a look at the fractions that it actually produces. Starting at the top of the fractionating column, where the temperature is lowest, we find the fractions with the lowest boiling points. These contain the smallest hydrocarbon molecules and include gases and petrol. Moving further down the column, we then find fractions such as kerosene, which is commonly used as aviation fuel, followed by diesel and fuel oil. Finally, right at the bottom of the column, where the temperature is highest, we find the fraction containing the largest hydrocarbon molecules. This contains bitumen, which is commonly used in road surfacing and roofing. Now, don't worry too much about trying to memorize every fraction and exactly where it appears in the column. The important thing is understanding the pattern. The further up the column a fraction is collected, the smaller the hydrocarbon molecules it contains and the lower their boiling points. Conversely, the further down the column a fraction is collected, the larger the hydrocarbon molecules and the higher their boiling points. If you understand that relationship, it becomes much easier to work out the order of the fractions rather than simply trying to memorize them. We've just seen that as we move down the fractionating column, the hydrocarbon molecules become larger and larger. And because the size of the hydrocarbon molecules is changing, a number of their physical properties change as well. The first of these we've already discussed. As the size of the hydrocarbon molecules increase, so do their boiling points. Larger molecules have a greater number of van der Waals forces acting between the molecules and therefore require more energy to overcome them. But boiling point isn't the only property that changes. The viscosity of the fractions also increases. Viscosity is simply a measure of how easily a liquid flows. Low viscosity liquids, such as petrol, flow very easily, whereas high viscosity liquids, such as bitumen, are much thicker and flow much more slowly. The volatility of the fractions, however, shows the opposite trend. Volatile substances evaporate easily, and since the smaller hydrocarbon molecules have lower boiling points, they require relatively little energy to enter the gas phase, making them much more volatile than the larger hydrocarbons. Finally, combustibility also decreases as the hydrocarbon molecules become larger. The smaller hydrocarbons ignite much more readily and also burn much more easily, making them excellent fuels. Larger hydrocarbons are much more difficult to ignite and therefore make less suitable fuels. Now, although these might initially seem like four separate trends to learn, they're actually all linked to the same underlying principle. As the size of the hydrocarbon molecules increase, the intermolecular forces acting between those molecules increases too. The greater number of van der Waals forces increase the boiling point, reduce volatility, and contribute to the thicker, more viscous nature of the larger fractions. So rather than trying to memorize each trend individually, try to relate them back to the increasing size of the hydrocarbon molecules. Before we finish, it's worth making one final connection. Earlier in your chemistry studies, you'll have almost certainly come across simple distillation and perhaps even fractional distillation in the laboratory. The underlying principle is exactly the same. Both techniques separate substances according to differences in their boiling points. The main difference is that industrial fractional distillation is designed to separate a complex mixture containing many different hydrocarbons, producing multiple fractions. Simple distillation, on the other hand, is normally used to separate a solvent from a solution or two liquids with significantly different boiling points. So although the equipment might look rather different, the chemistry behind both techniques is exactly the same. So crude oil is a complex mixture of hydrocarbon molecules that can be separated into useful fractions by fractional distillation. Each fraction contains a mixture of hydrocarbon molecules with similar boiling points and therefore has a particular use. The process of fractional distillation works because different hydrocarbons have different boiling points and the fractionating column contains a temperature gradient. This allows different hydrocarbon molecules to condense at different levels within the column. Small hydrocarbon molecules have low boiling points and are collected near the top of the column, whilst large hydrocarbon molecules have high boiling points and are therefore collected towards the bottom. In terms of trends, as the size of the molecules in each fraction increases, so too do the boiling points and viscosity. However, volatility and combustibility decrease. As such, not every fraction produced from crude oil is equally useful. Some of the fractions containing larger hydrocarbon molecules are produced in much greater quantities than what is needed to meet demand, whilst the more useful shorter chains aren't. And this leads us onto the process of cracking, which we'll be covering in detail in the next video. And as always, the full topic playlist is on your screen now. And if you found this video helpful, please consider subscribing for continued support with A-Level Chemistry.